Okay, today I'm going to talk to you about the chain rule. Now, firstly, I just want to talk about a couple of things that will help you with this lesson today, because this is a little bit harder than most of the things we've done so far. Okay, now, the first thing is the notation. Okay, now I'm going to use slightly different notation today because it helps you to understand why we use the chain rule and how it works. Okay, now, firstly, when we talk about functions, we normally talk about them as function of x, fx. That is the function in terms of x. Okay, we also then say that the differentiated function, okay, the first derivative is f prime x. All right, we can also write this as y or y prime. Okay, there's another notation that we can use, and that is when we have y, if we differentiate it, we can write it as dy dx. Okay, and that's quite similar to the notation you've used before. If we had a straight line, that looked like this, for example, and we wanted to know the slope of the line, okay, we would look at delta y over delta x. Okay, we would say slope is delta y over delta x. Okay, this is slope. Now we use dy dx in place of delta because we're not actually looking at the slope of the line consistently. Okay, we're looking at a slope function. Okay, so this is the notation I'm going to use today just to show you how the chain rule works. Okay, the next thing is I want to talk about what the chain rule is used for. Okay, now normally we have been working just with functions. So for example, function of x equals x squared. Okay, this is a function. The chain rule is used when there is a function inside another function. Okay, so that means we have, for example, the function of, instead of just an x being inside, we have another function. So the f gx. Okay, so you can see, and I'll do this in another color, that we have another function inside the first one. Okay, so an example of a way that we could write this first function as a chain, or as a function that requires the chain rule, would be that we can say function of x is equal to, and instead of x, we're going to put a function there. So we're going to say, for example, 2x plus 3 squared. Okay, so this is a function inside another function. The first function is this one, okay, and it is inside the function of x squared, for example. Okay, now with the chain rule, it's quite straightforward, but what I'm going to do is go through how to apply it in a longer way so that when we start using it with more complicated rules, that you're able to do this. Okay, so when we start using this in combination with the product rule and the quotient rule, it can get a bit more complicated. Also, when we start doing this with trigonometric functions later. Okay, so let's look at the one we just wrote down. So we have fx is equal to 2x plus 3 squared. Okay, and as I said, we're going to look at the chain rule. Now, this fx is the function in terms of x. Okay, now what we're going to do is we're going to start firstly by saying let u equal 2x plus 3. Okay, so we're going to say let u equal 2x plus 3, and 2x plus 3 is just what's inside the bracket. Okay, this is going to be u. So now instead of having a function in terms of x, we have a function in terms of u, which is just going to be now u squared. All right, so this is now our function in terms of u. Now, we need to differentiate this. Okay, now what I'm going to do though is, as I said, I'm going to use the different notation. So let's just write over here just to show you how this works. Let's say that we have now, originally we had originally we had y equals 2x plus 3 squared. Now we have y equals u squared. Okay? Now, if we differentiate this, so if we differentiate y equals u squared, we get dy, and instead of dx, it's going to be du. Okay, so it's going to be, if we differentiate this, 2u. Okay, what we are looking for is, we wanted to differentiate the original term, so what we are looking for is dy dx. This is what we're looking for. This is what we're trying to find. Okay, now, so if we want dy dx, and we can calculate dy du. So dy du, we are able to calculate here. All right, we need to think of a way to get dy dx instead of dy du. So how can we get rid of this du? Well, what we can do is we can multiply this by du dx. Okay, and what this means is that we're differentiating u in terms of x. Okay, so we could actually do that because we have u. All right, so we said way back here that u was equal to 2x plus 3. So if u equals 2x plus 3, then du dx is just going to be equal to 2. Okay, and as I said, for this one, this is not the most efficient way to do this, but this is more about you guys learning the process. So now, dy dx, so what we're finally looking for, this would be the first derivative, is equal to dy du. So we have that here, dy du is just this one here. Okay, times du dx. And du dx is this one over here. Okay, so dy dx, so the derivative is equal to dy du, so du times du dx, which is 2. Okay, so we just get 4u. All right, and our original function did not have a u in it. It had 2x plus 3, so then we just substitute that u back into here, and we're going to get 4 2x plus 3. Okay, so this is dy dx, okay? Or alternatively, this is f prime x, if you prefer that notation. All right, so that's pretty confusing for the first time. All right, so let's go through it again with another example. So if I gave you y equals 2x squared plus 3x to the power of 4. All right, and what I'm going to do now is go through the real structure of how to do this. Okay, so the first thing we do is let u equal 2x squared plus 3x. Okay, so the first thing you should then do is, the next thing you should do, is write y equals, and then replace that 2x squared plus 3x with u, so u to the power of 4. Okay, then all we need to do is differentiate each of these. So we get du dx is equal to 4x plus 3, and dy du is equal to 4u cubed. Okay, now remember our formula, dy dx is equal to du dx times dy du. So then we just multiply those two things together that we just calculated, because du dx is here and dy du is here. Okay, so multiply them together, we get 4x plus 3 times, and in this case I haven't given myself enough room, 4u cubed. Okay, so this is dy dx. Now we want this without a u in it. Okay, so it's equal to 4. U was 2x squared plus 3x. Cubed times 4x plus 3. Okay, and that's it. We're done. So let's do another example just to make sure. So let's say that we had y is equal to 6 4x cubed plus 3x squared plus 2x to the power of 7. All right, and we want to differentiate this. So let u equal 4x cubed plus 3x squared plus 2x. Okay, du dx is equal to 12x squared plus 6x plus 2. All right, y in terms of u is equal to 6u to the power of 7. So dy dx is going to be equal to 47u to the power of 6. All right, dy dx is equal to du dx times dy dx. Well, what did I do? dy du. Sorry, this should have been a u back here. Okay, and I think way back here I might not have shown you why we were able to do this, because over here when you're multiplying these you can see that we can cancel the du's out and we get dy dx left. Okay, my apologies for not mentioning that. So if we cancel the d, we can do this and then cancel the du's, and what's left is the dy dx. Okay, so du dx was 12x squared plus 6x plus 2, and dy du was 47u to the power of 6. Okay, we're going to simplify this, so we have 47, because remember we always put the coefficient first. U to the power of 6, so u was 4x cubed plus 3x squared plus 2x to the power of 6 times 12x squared plus 6x plus 2. And we're done. Okay, so this is how we use the chain rule. Okay, in the future you will be doing this in combination with the product rule and the quotient rule, so please get very familiar with this and make sure you also practice the product and quotient rule separately.